We have a new topic for discussion today, and that is image segmentation. Now, image segmentation process generally refers to making different parts of the image, or rather breaking up the image into its constituent parts or objects. Okay, rather it's a subdivision or partitioning which we do based on some properties of the object. Now, in an image usually what we find is that there are several objects which are present. All right, supposing this is an image, and there may be an object of this nature, there may be another object of this nature, there may be some other object of, say, this nature, and there is also some background which is available. Now, our task is to extract these objects very properly. Means if the image is of a good quality, all right, then there is no difficulty in identifying all these three objects individually. All right. Now we can do it by our own eyes. Okay. By clearly seeing these three objects, we can conclude that which object is of which nature. That means to say, we can classify the object number 1, the object number 2, and the object number 3 from our own knowledge and experience. But now the task which we are going to have here is that how to automate this process so that instead of a man doing it through his or her eyes, okay, how a computer will be able to do this. Okay, that means to say, this kind of a subdivision, or rather partitioning of an image, okay, which we are going to do, if that can be done automatically, okay, in a very nice fashion, then after detecting the various objects, okay, we can identify or rather classify it into several known objects, several known objects of interest. Now, in an image, there are certain objects of interest to us, okay, and even the interest also may be to varying degrees, okay, or varying levels, okay. All right. Let us consider some examples. Supposing, let us take an industrial environment, all right, where we are going to identify the various tools which are lying on a tray or a bin. Let's say we have a bin like this. Supposing this is an image, okay, and we have a bin over here on which some tools are kept. Supposing this is an application where we are using a robo for doing the assembly operation. Okay, there are various tools which are available on the bin. Okay, maybe some wrench, some pliers, some saw, and all these various items are available on a tray. And we have a computer vision system associated with the robo, whereby using that computer vision system, okay, using the camera, we can capture the image of this entire thing. Okay, that means to say the tray containing all the various tools. Okay, and then we should be able to identify the individual tools so that we can instruct the robo to pick up the tool of interest. Okay, and then if it will pick up the tool or the object of interest, and then it will do the assembling operation. All right. These can be for various tools, this can be for various machine parts, etc. All right. So essentially what we have is that we must have a system whereby we can identify the various objects. Now this is lying in some, the tools are lying on a tray, and there is also some background which is available, and maybe that there are some other objects, okay, within the field of view of the camera, there may be some other objects here, there, okay, but we are not interested with all these objects. We are only interested with the objects which are lying on a, which are on this beam. So what we will have to do is that at first we will have to identify this beam. Okay, we have to extract this, okay, from its background. Okay, once that is extracted, we can forget about the rest of the things, all right, which are there in the image. Now then, we will concentrate on this particular beam, and then we will identify the individual parts, all right. And in this case, our object of interest, or rather our intention, is only to identify the various tools or the various machine parts. Okay, we are not really concerned about the dimensions of those machine parts, or whether the tool contains any missing part or not. All these various details we are not interested with. We are only interested in identifying that, okay, a cutter should be identified properly. It should not be mixed up with the scissors. Okay, we must have a definite. Rather, the object should be detected with a good amount of confidence. Okay, but we are not interested with the too much of details. So what we will now do, we will once again partition the image, or rather this time we can do it for the beam only, and then we can go to the extent of detecting the object only. Now there may be some applications where, supposing it's an application of industrial inspection, where we are inspecting the dimension of some tools, let's say, okay, or dimension of some machine parts. Now in those cases, okay, just identifying the object alone will not suffice. We must also find out all its internal details. All the details which are available on the object, okay, which can be sensed by the camera, okay, must be well understood. Okay, so the level of partitioning or the level of image segmentation which you would like to do, that depends upon the application. There are some applications where you can afford to go with only up to a limited level of partitioning, and there are some applications where you may have to go to a detailed depth, or rather the levels of partitioning may be much higher in some other applications. Now basically in the image segmentation portion of this course, okay, we will be studying that how exactly we go about segmenting the images. All right. Now generally two approaches are followed. So we can classify the image segmentation approach into two known classes. Okay, the first is through detection of discontinuities in the image. Okay, so that is to say, where to do the segmentation we detect the discontinuities in the image. Discontinuity means what? Discontinuity in the image means variation in pixel intensities. And why or where should we have variation of pixel intensities? At the boundaries, obviously. When we have one object over here, okay, and then very clearly this object will have some intensity value and the background will have some other intensity value, and at the boundaries of this object, okay, there are some discontinuity which is there in the pixel intensity. Okay, so in the segmentation approach based on discontinuity, we will be detecting the edge pixels, or rather we should be able to clearly identify the boundaries of an object. Just detecting the edge pixels alone will not suffice, because edge pixels, there may be several edge pixels. There may be some edge pixels which are really wanted, which are the boundary points of an image, and there are also some edge pixels, okay, which only correspond to noise and which cannot be linked properly. So these are the things which we should see, that it is not only the edge detection alone, but we should be able to do a very proper and appropriate grouping of the edge pixels. Alright. Rather, here what we are interested in doing is that we must detect the discontinuities in the intensities in order to very clearly detect the object boundaries. The second approach which is followed is segmentation based on similarity of pixels. Okay, this approach is entirely different from the discontinuity based approach, because discontinuity means we are clearly seeing the dissimilarities between the pixels. I mean, where there is a clear discontinuity happening, whereas in similarity what we will be doing, if somebody gives us an image like this, maybe that this object has got some intensity level. Supposing we are assuming that all these three objects have their own intensity levels. Supposing that this object is having intensity value f1, this object is having intensity value f2, this object is having intensity value f3, all of them assume that they are uniform intensity, and supposing the background is having some other intensity value f4. Alright. Now, if we choose the pixels, okay, which are lying within this object, all of them are having a good similarity in the pixel intensity. All of them are having intensity equal to f1, or actually absolutely uniform intensity condition is somewhat ideal. In practical images we may not get such kind of absolute uniform intensity. I mean, there are variations in the lighting, there are noise in the image capturing process itself, there may be some variations in the object itself. I mean, there may be some marks or other things on the object itself, so that some amount of non-uniform intensities will be there. So, okay, let us assume that f1 plus or minus some tolerance intensity, okay. If you find that all the neighboring pixels, okay, are having such similarity of intensity values, f1 plus or minus some tolerance, okay, then all those similar pixels you group together, and wherever you find that similar pixels are no longer there, you declare that they are not in those similar regions. So based on such similar pixels you form a region, okay, and that region you characterize as a image partition or an image segment. Alright. Very similarly for f2, for f3, for the background f4, okay, you can detect the partitions based on similarities in the gray level values, okay. Now for that, the approach which we normally adopt is that we can find the histogram of an image. Alright, let us say we form an histogram. Supposing the histogram is something like this. Histogram means on the x-axis we have the pixel intensities, okay, and on the y-axis we are having the number of pixels, or rather the population, number of pixels, or rather the population of pixels we have in this axis, and then we can subdivide this histogram, okay, into a few known zones. Supposing we separate it into 1, 2, 3, 4 known zones are there, okay, and then we can group all the pixels which are having intensities all similar in this region, or intensities which are all similar in this region. Like this we will be able to find out that which region is what, okay, especially wherever we have images having images like this, alright, f1, f2, f3, f4, okay, then you may get a multimodal histogram. I mean, it could be something like this. Alright, so maybe that we have these many pixels for intensity level f1, this many pixels for intensity level F2, this many for intensity level F3, this many for intensity level F4. Alright. Now what we will do, we can choose the threshold in such a manner that we will declare all the pixels in the having intensity F1 plus or minus some values, okay, to be of region 1, this to be of region 2, this one as region 3, and the last one as region 4. Okay, like this we can have various partitions. Okay, now this is a very simple case where we have a multimodal histogram, and we can separate, okay, very clearly the objects of interest. Okay, but wherever we have, we don't have such prominent peaks, okay, in the histogram. Okay, this approach may not work that effectively, but still these are used. Or rather, the threshold detection is not the only technique to find out similarities. There may be other approaches towards similarity detection also, like region growing, okay, and then region splitting and merging, and all these techniques we are going to discuss, okay, during our segmentation, our lectures on segmentations. Okay, so we will first start with segmentation approaches based on discontinuities. Now, before we go over to discontinuity based image segmentation, I'd like to point out one or two other things. Like, we normally consider static images, or rather we normally consider still frames of images where we have a single frame available with us, and from that image we are interested in finding out all the similar regions, or to partition it into some different blocks. Okay, all these things we would like to do for the static images, but many a times instead of static images we have dynamic or moving images. Okay, like say for example a sequence of images which we are getting from a video. Okay, in such cases we can not only apply this discontinuity based segmentation and similarity based segmentation, both these techniques we can very effectively apply, but in addition to that we can also apply the motion cues. Okay, motion cues means where an object is changing its position from frame to frame. Okay, then if we can detect some moving object, then we can also partition that moving object from the rest of the image. So motion actually provides a very important cue for image segmentation. All right, and let me tell you that image segmentation is usually an essential component in many major applications of image processing. Like say for example, take the case of automated target detection. All right, supposing somebody has given you an infrared image, all right, and from that we are going to detect the tanks or missiles. All right, now here what we are going to do, that from that image we are going to separate the actual object of interest from its background. In an infrared image what will happen is that since the tanks are quite hot bodies, okay, their intensities will be higher as compared to the other objects, okay, which do not have such kind of thermal outputs. All right, and as a result of that, from those thermal or infrared images we will be able to identify that which portion belongs to target and which portion belongs to background. So for target identification, prior to a target identification, image segmentation is a must. In automated industrial inspection application, okay, when you are inspecting an object, okay, finding a very clear boundary of the object is an essential portion. Okay, and that you can only do if you can segment the image properly. All right, let us say the applications of remote sensing images. Okay, we have a satellite image. Okay, satellite image of a particular region. Now just that satellite image alone is not of interest to us. we are really interested in finding out the various zones in the image. That's to say, which region corresponds to the crop area, which region corresponds to the vegetation, and all these things. I mean, if we have the image of a region like this, all right, we will be interested in finding out the various portions which are present in the image, and not only that, we should be able to identify that which zone corresponds to what. Okay, and we can only do that if the image is very well partitioned. All right. So a very well partitioned image, or rather segmented image, is definitely a must in many major applications of image processing. Now the question is that how effectively we can do this image segmentation. Supposing we have a very poor contrast image. All right. Supposing we have taken an image under a very poor lighting condition and nothing is visible much. Okay. If the input image itself is so bad, okay, then even finding out the objects of interest will be problem. Sometimes we have seen that even with our eyes we cannot detect the objects if the photographic conditions are too bad. If the illumination condition is too bad, we cannot do that. So definitely the quality of the image is very important. Firstly, that in some images, okay, we have a controlled environment available with us where the lighting is under our control. We can place the object against a good contrast background. Okay, let us take the example of industrial machine vision. All right, where we definitely have a fixed table where the object will be placed. Okay, and then we can have the lighting as per our choice exactly. Okay, and then we take the image under a very controlled environment. So if the image quality itself is good, then we can take the it will be possible for us to do a better segmentation definitely. Now say for example there are some applications where the environment is not under your control, like infrared image. All right, you don't have any control over the environment. Now what you can do there is that at least try to use sensors, okay, imaging sensors, okay, which are quite sensitive enough, okay, which can enhance the objects of interest against its background. Okay, and if we can use a better quality image, then we can do obviously a better segmentation or partitioning. Now we will start with the discontinuity based image segmentation approach. Now, in discontinuity based image segmentation, what we do is that we have to first detect the edge pixels. How do we do that? The techniques are well known to us. Okay, we can apply any edge detection technique, okay, whichever we have read. Okay, all these, any edge detection technique we can apply and get what? We get a set of edge pixels. Okay. Now the set of edge pixels, obviously we cannot call them as the object boundaries. Okay. We may be getting, supposing this is our image and we are getting some edge pixels which I am marking with cross. Like this, we will be getting set of edge pixels. Now what we do, there are some edge pixels which correspond to some object boundaries, okay, and there are some edge pixels which do not. Like say for example, if we have an edge pixel like this, okay, very clearly this does not belong to any object, or some isolated pixels like this. This also is not corresponding to any object. This is an isolated, but very clearly we can make out that all the other edge pixels, okay, they correspond to some object boundaries. So if it is possible for us to start with some edge pixels, let's say we start with this edge pixel, and then we find out that we have a very similar edge pixel lying on its neighborhood, okay, we can just join them, and then we find that there are some other edge pixels ahead, okay. Like this we can track, we can keep on tracking the edge pixels and get a boundary like this, and thereby we can conclude that obviously this is going to be the edge pixels, or rather these are going to be the boundaries of some object. Now there are some cases where because of poor lighting condition, okay, it may not be possible to detect the object boundary very clearly. Let's say we have an we have a set of edge pixels like this, so we try to group them like this, we keep on grouping, and here we find that there is a very clear discontinuity, okay. Maybe we are having 1 or 2 pixels over here, but we find that these cannot be joined directly because this edge pixels and this edge pixel, they are not in the immediate neighborhood of this one. That means to say there are some discontinuities in the edge pixels, okay. But if we have such kind of discontinuities, or rather some gaps present in the edge boundary, okay, we must know how to bridge those gaps, all right. Such techniques also should be known to us, okay, so that we can bridge the gaps and form the object boundaries very clearly. Now the approach which we should follow is that at first we apply some edge detection technique and get a set of edge pixels, and then we start with any known point, all right. We take, supposing we have an edge pixel on this grid, okay, consider the grid which is given here, and supposing we have an edge pixel lying over here, okay. Now in order to do an edge linking, okay, what we have to do, we must investigate the edge pixels surrounding the pixel which we have considered, all right, and we define some small neighborhood. Let us say we define a neighborhood of 3 by 3 pixels or a neighborhood of 5 by 5 pixels over which we are going to search if we have a very similar edge pixel present in that neighborhood. Supposing we consider a 3 by 3 neighborhood. So if we start from this point, we will consider a 3 by 3 neighborhood, which I indicate here with the dots, and then we will examine that out of all these dots whether any pixel is an edge pixel. Supposing we find that this pixel is going to be an edge pixel, so we try to form a group. This pixel and this pixel, we can form a group, but can we do it always? Many a times what we will find is that the edge will change in its direction, or the edge will change in its strength, and this is very much possible where the neighboring edge pixels correspond to different objects, different object boundaries, all right. So while linking the edges, it is also important that we should link the edges only if their edge angles match and their edge strengths are very similar to each other. So that means to say we are going to study the similarity property of the edge pixels within a 3 by 3 or a 5 by 5 or any defined neighborhood. So we find, supposing we find that there is yet another edge pixel, okay, which is having a very similar edge angle and a very similar edge strength. So we can put them, I mean we can maintain a record, okay, or we can maintain a list, okay, whereby we can store all the edge pixels, okay, which can be linked in a very similar way. Supposing we find that after this point we detect that there is yet another edge pixel over here, and supposing from this edge pixel we find that we have an edge pixel over here like this. Now very clearly the edge angle has changed. So what we will do, we will link up the edge pixels only up to this point, alright, and from this point onwards an entirely new linking should begin, alright. So all these 3 pixels will be linked together, we call it as link number 1, okay, and then from this pixel we are proceeding and we will be having a link number 2. Like this we will be having different groups of edge pixels, alright, and the grouping, or rather the clubbing of the edge pixels, okay, which we are doing. This is done based on 2 definite criteria. The first criteria is the edge strength. And in edge strength what we do is, if we have 2 pixels, say defined at positions xy and x prime y prime, supposing we have 2 pixels xy and x prime y prime, then if their intensity values are fxy and fx prime y prime respectively, then how can we measure the edge strength? How do we measure the edge strength? We normally use the gradient operators, okay, for the edge detection, isn't it? Either a first derivative or a second derivative. But when we would like to measure the edge strength, we do it by computing the gradients. So we apply a horizontal edge detection mask, we apply a vertical edge detection mask, okay, and supposing the horizontal edge detection mask is having strength fx, okay, we take fx square, and supposing the vertical edge detection mask is having a strength fy, then we take square root of fx square plus fy square, and this gives us the edge strength at that point xy, okay. Now what we will do is, we will compare the gradients of xy and x prime y prime, the magnitude of the gradients, okay. Supposing the magnitude of the gradients we normally denote by this, del f xy, and this we see del f xy minus del f x prime y prime, and the magnitude of this, okay, should be less than or equal to some value t, okay, where t is a non-negative threshold. T is usually a small value, so that we will be grouping the edge pixels which are having very similar gradient intensity values, or very similar edge strengths or gradient magnitudes, alright. So that is the criteria number 1 for grouping. And the second criteria for grouping is that the edge angles, okay, must be very similar, okay, or rather by considering the direction of the gradient. How do you measure the direction of the gradient? Supposing the edge strength is fy in the y direction and fx in the x direction, tan inverse fy by fx, okay, that gives us the direction of the gradient. So we also find the direction of the edge, of the gradient, call this angle as alpha, okay, so that we will be considering the value of alpha at the point xy and take its difference with the value of alpha at the point, at yet another point x prime y prime. And if the magnitude of alpha xy minus alpha x prime y prime is less than some threshold a, okay, then we can say that the two edge pixels xy and x prime y prime can be linked up. Okay. So based on the edge strength, so the two criteria are edge strength and edge angle, based on which we can link the edge pixels. So like this, we have found one link to be 1, the second link as number 2, and like this there can be a number of such chains of edge pixels which can be formed, right? And in order to do a boundary detection, we can do the boundary detection only by examining all these different links, okay? Supposing the boundary of an object is of this nature. Now this may be formed by this as the link of edge pixels 1, okay, link number 1 consisting of several edge pixels. This is link number 2. This has become link number 2 because the direction, the edge direction has changed, okay. This as link number 3, link number 4, link number 5, 6, 7, okay. Like this, we can examine all these links and find that since their endpoints are similar, supposing we find that the endpoints of link number 1 and the endpoints of link number 2, okay, they are having one common point, okay, we can say that link number 1 and 2, okay, they can be joined together, or rather they form the boundary of an object. So like this, one can clearly distinguish the boundary of an object, all right. And while joining such edge pixels, okay, we must also see that if there are some small gaps, say within a neighborhood of 3 by 3 pixel or 5 by pixel, if there are gaps of 1 or 2 pixels, okay, then also we can attempt to bridge those gaps. That means to say, supposing we consider that there is 1 pixel over here, okay, and there is no pixel, no edge pixel in the immediate neighborhood, but there is yet another pixel over here which is having a very similar strength and direction, okay, then we can link them together, okay. And that way, to a limited extent, if the gaps are of smaller size, okay, we can bridge those gaps, all right. So this is one approach which is followed for edge linking, and this approach is called as the local edge linking approach. Okay, or rather a local approach towards boundary detection. Why do we call it as local? We are taking a 3 by 3 or a 5 by 5 neighborhood, okay, and we are examining only the edge pixels present within those local neighborhoods. Of course, we are going to carry out this operation over the entire image, or rather for every edge pixel we have to do this operation, but still at a time we are considering only a local area, and that is why this approach is called as local edge linking. Now in this case, what we have to do always is that we must record all these grouped edge pixels into some list, okay. That we have to ensure. Now, another approach could be a global approach towards edge linking. Okay, and the problem is something like this. So we are now going to consider global edge linking. Supposing we have got n number of points. So supposing there are n number of edge pixels, and our interest is to find out that out of these n pixels, which subset of pixels belong to a straight line of interest. Okay. Now, just see that this problem is, this problem can be tackled like this, that we consider any particular point, okay, and we try to form pairs of this point with all the other points. Okay. Like this we can form pairs with all the other points, and in that case, how many such lines we can form? If from every point we join other pairs, there will be totally n into n number of 1, n minus 1 divided by 2. So many number of different straight lines can be formed. And then for every such point, we have to examine that which one of these straight lines, okay, correspond to the straight line pertaining to the object. So that means to say the n into n minus 1 by 2 itself means that there is a such complexity of the order of n square. And then if this is to be done for every point, then there is order of n cube number of searches which are involved. Okay. So this is obviously a, computationally this approach is having a prohibitive cost. So we should look for a different and easier approach towards a global edge linking, and that we can do by using half transforms. We are going to discuss about this approach, half transforms, in the next class. Any question? Thank you.